We have Brian CHMIEL from Habana Labs in Technion, and he'll be presenting neural gradients, optimal lognormal, improved quantize and sparse training.
Again, hi, I'm Brian. I'm a researcher in Habana Labs and a PhD student in the Technion. I will present to you the work neural gradients are lognormal, improved quantize and sparse training. It was presented last month in ICLR. So we can look at the training process. We start from training data X and multiply that from some weights W and get the activation and so on until we get some loss function. And then we start the backpropagation process, of course, when we see two kinds of gradients, which the neural gradient, it's the derivative of the loss with respect to the input. And we have, of course, the weight gradient, which is the update of the weights. And we can see that a lot of work that focus on quantization of pruning, and most of them focus on the weights and activation, and they use an approximation of normal distribution to find the optimal threshold for pruning or the clipping value for the quantization. But most of the work don't look at the neural gradients, and we know that they're a big bottleneck for training because they participate in 2 of the 3 main multiplications in the training process. And we find in this work that the main reason that previous works not works on the neural gradient is that they suffer from different statistical properties. And we find that log-normal distribution is a good approximation for the neural gradients. So first of all, to check the goodness of this fit, we use the economorphism of test, which calculate the maximum distance between the CDF of the theoretical function and the data. And of course, as shown here in many data set and models, log normal distribution is a very good fit for the neural gradients. So in this work, we take this estimation, the bigger estimation of the log normal distribution, and use it for 2 different tasks, for quantization and pruning. So in the quantization part, we focus on floating point quantization. And one of the problems in floating point quantization, especially in low bit, how we would find the optimal allocation between the exponent and the mantissa. There is no standard for low bit floating point. And we using the work as the measure the relative error here presented, and assuming the log normal distribution for the neural gradient, we find an analytical closed formula that minimize it. We can find what is the optimal allocation for the exponent and mantissa for the neural gradient. And of course, we run it in many networks and different data types of floating points. And in all the cases, we get the best result with the optimal exponent that we found. And the second task that we show in this work is for pruning. More specifically, we use what is called stochastic pruning, that it has 2 different thresholds. We have a regular threshold alpha, and additionally, we have a stochastic value epsilon, which is uniform distributed. And what the stochastic pruning do, it all the values between 0 and alpha epsilon goes to 0, but all the values between alpha epsilon and alpha, we increase them to alpha. So in that way, we keep the mean, the expectation of the tensor. And here again, one of the problems in pruning is you want some threshold, but you don't know what is the you want span sparsity, of course, but you don't know what is the threshold that will induce your required sparsity. So here again, we use the log normal distribution and found a closed formula. And of course, we show in the work that we are able to achieve the required sparsity. And we compare ourselves with many previous methods that use pruning to the neural gradients, and we show state-of-the-art results.
Have you done any simulations to see how it compares to perhaps doing your computations fixed point?
Yeah, of course, we have in the paper. And in training, because the distribution of the neural gradients, fixed point is it's not good choices. We need a representation that have a very long range. So floating point is a better representation for the gradients.
Okay, thank you, Brian.
I want to thank our sponsors that made this event possible. So the premier sponsors, Newton, working on automated TinyML. If you were there a few days ago, they had a keynote explaining what they're doing. Executive sponsors are ARM, Edge Impulse as well, and Qualcomm, Sentient, and then our platinum sponsors. We have Infineon and Reality AI. Gold sponsors are Latent AI, SensiML, and our silver sponsors are EMEA, Greenwaves, HOTG, ImageNet, GISO, SEED, and ST. And with that, I thank you very much for staying on till the very last end, the last day of the last session of the last day. And with that, I think we can close the forum for this year. Thank you everybody for contributing. Thank you, Andreas, for also moderating this session.